In this video, you'll be introduced to lift. The concepts discussed in this video will explain how surfing with a business card is possible. More importantly, lift explains how humongous aircraft can carry tons of humans and cargo to high altitudes and land, more often than not, on time at their destinations thousands of miles away. From an underwater robot's perspective, the concepts in this video will enable you to understand how a propeller generates thrust underwater. Before getting started on lift, think back to the video on drag forces, where we discussed sticking hands out of car windows. A hand hanging out of the car window in this orientation will experience a pure drag force. In the video on drag, we showed how a hand can be approximated with a flat plate. Using the flat plate approximation, the drag equation and the coefficient of drag were introduced. Drag was defined as a net force that is parallel to the upstream flow due to pressure and shear forces on the surface of an object. You were also introduced to the reference area and the drag coefficient. Let's go back to thinking about sticking hands out of car windows at freeway speeds. If you've done this, think about how it felt to orient your hand in this manner. You might have felt a force pushing your hand up, as well as a drag force pushing your hand back. You now know all about drag, so now let's discuss the force pushing your hand up. Again, we can approximate a hand as a flat plate. Here is the two-dimensional view of the flat plate. The flow is moving in the positive x direction, which is to the right. The positive y direction is pointing up. We can define an angle theta, which you see here. Theta is 0 when the flat plate is in this orientation. If you recall, the stresses due to pressure on the top and bottom of the plate are balanced in this orientation, and there are no forces on the plate that move it up or down. Theta is 90 degrees when the flat plate is in this orientation. If you recall, the difference in the pressure forces on the front and back of the plate are not equal, and a pure drag force is experienced in this orientation. There are no forces on the plate that make it move up or down. The angle theta is called the angle of attack. A flat plate at an angle of attack between 0 degrees and 90 degrees will experience a difference between the shear forces on the front and back sides of the plate. Pressure forces on the front and back sides of the plate will also be different. These differences in pressure and shear forces will result in a drag force on the plate. Recall that drag is a net force that is parallel to the upstream flow due to pressure and shear forces on the surface of an object. But the differences in pressure and shear forces also give rise to a lift force. Lift is a net force that is normal to the upstream flow due to pressure and shear forces on the surface of an object. The lift equation appears similar to the drag equation. Here, rho is the density of the fluid in kilograms per cubic meter. V is the upstream velocity in meters per second. C sub L is the lift coefficient. It can be determined experimentally. The effects of both shear forces and pressure are considered together in the lift coefficient. At this point in time, you may be wondering why the lift equation does not consider angle of attack. Well, it does. This is because the lift coefficient is a number that is used to model all of the complex dependencies on the lift of an object, which includes shape, flow conditions, and the inclination of the object. As an example, here you see a graph of angle of attack versus lift coefficient for a flat plate. At a 0 degree angle of attack, the lift coefficient of the flat plate is 0, and therefore there is no lift. At an angle of attack of 3 degrees, the coefficient of lift on the flat plate increases to 0.25. At an angle of attack of 7 degrees, the coefficient of lift on the flat plate increases to 0.7. At 9 degrees, the lift coefficient is nearly maximized at 0.75. And at a relatively high angle of attack of 15 degrees, a more complex flow occurs on the flat plate, resulting in a decrease in the lift coefficient to 0.7. Therefore, the lift coefficient, as well as the lift force, for a flat plate is maximized at an angle of attack of about 11 degrees. Maximizing the coefficient of lift at low speeds is the reason why airplane wings change form during landing. This slide is an example of how the lift coefficient and drag coefficient are used to model the complex dependencies on the lift and drag of an object, which include shape, flow conditions, and inclination. In this graph, you can see that the coefficient of lift can be increased at a certain angle of attack just by changing the shape of a wing. However, there is a trade-off. Wing shapes that generate a lot of lift also generate a lot of drag, since the coefficient of drag also increases with coefficient of lift as the shape of a wing is changed. Now, getting back to the lift equation. A is the reference area, in units of square meters. Knowing which reference area to use in fluids problems is very important, since reference area can be different when calculating lift and drag. We will focus on reference area in the next video. Note that the lift and drag forces act on a point on the flat plate. This point is called the center of pressure. Therefore, a resultant force arises from the lift and drag forces acting on the flat plate, and this resultant force acts on the center of pressure of the plate. This is why when you stick your hand out of the window of a moving car in this orientation, you don't just feel a force pushing back or a force just pushing up, but rather a force pushing your hand in the direction of the resultant force. Note that the center of pressure on an object can be at a different point than the center of gravity. In this slide, you can see how the center of pressure on a wing can change with angle of attack. This is particularly important in the application shown here. Here you see a P-51 Mustang taking off. The plane generates thrust, accelerates, and acquires a velocity that overcomes drag forces and enable the wings and other surfaces of the aircraft to generate lift, which cause the plane to take off and fly off into the wild blue yonder. Isn't fluids exciting? Now, let's take a look at what generates thrust on this aircraft. The concepts that you've learned thus far can explain how propellers and turbine blades work. This is because propellers and turbine blades generate aerodynamic forces in the same way as wings. Notice that the propellers of a P-51D Mustang are twisted. Why is that? Well, blades are twisted to maintain equal thrust along the blades. For an object rotating about an axis, every point on the object has the same angular velocity. However, the tangential velocity of any point is proportional to its distance from the axis of rotation. The relative airflow is therefore different from the hub to the tips. Because of this difference in airflow, propellers and turbine blades need to have different angles of attack as well as different shapes in order to maintain equal thrust along the blades. If the propeller blades were not twisted, but rather were held at a fixed angle of attack from the hub to the tip, then you would have different thrust generated from hub to the tip, which would not be optimal. This is why the turbine blades that you will be using in your underwater robots are twisted. Next time you are in the lab, take a look at the blades on the thrusters of your underwater robot. This is also why the blades are twisted in the turbines used to generate wind energy. In this video, we focused on lift. Remember that the angle of attack is the angle between the chord of an object and the direction of the surrounding undisturbed flow of gas or liquid. Unlike the drag force, lift forces are normal to the upstream flow. Furthermore, the lift coefficient can be used to model all of the complex dependencies on the lift of an object, such as shape and angle of attack. We hope that you think about these the next time you take an airplane flight or watch your robots propel themselves through water. Now let's take a quiz. Let's go back and discuss the bus hatch that was presented in the quiz in the previous video on drag. Recall that the bus was traveling at 27.78 meters per second, and the square hatch had sides with lengths of 0.5 meters. Assuming that the hatch can be modeled as a flat plate with a reference area of 0.25 square meters, what is the maximum lift force that can be generated by this bus hatch? You will be needing the following information, and your choices are shown on the left. Please pause the video, work out this problem, choose a solution, and unpause the video to see the solution. The answer is 88.98 newtons. All of the concepts discussed in this video are essential to this problem. Based on the information given on the graph, the lift coefficient is maximized at an angle of attack of about 11 degrees for a flat plate. This lift coefficient is about 0.75. The density of the air is given as 1.23 kilograms per cubic meter, and the velocity of the bus is 27.78 meters per second. These go into the lift equation. For lift, we use the planned form area of the flat plate, which is 0.25 square meters. Plugging these into the lift equation results in a maximum lift force of 88.98 newtons.